Beyond Pluto, far past the last known major planet, astronomers believe something enormous may still be out there. A hidden world, colder than ice, darker than space around it, moving so slowly that no one has ever seen it directly. If it exists, it could reshape everything known about the outer solar system. Before continuing, please like the video, subscribe to the channel, and join this journey into one of the strangest mysteries in space, the giant planet that may be hiding beyond Pluto. Far beyond the bright inner regions of the solar system, the Sun still holds a vast and quiet domain together, past the orbit of Neptune and past the colder path followed by Pluto. Sunlight weakens until it becomes a thin and distant glow. The warmth that shapes the surfaces and atmospheres of the nearer planets fades almost completely. Motion remains, but it slows into long, patient arcs. Matter remains, but it becomes rare, scattered, and difficult to see. In this remote frontier, the solar system no longer appears as a compact family of worlds circling close to their star. It opens into a sparse gravitational landscape, broad enough that distance itself becomes the main feature. At such ranges, the Sun is still the central master of motion, yet its rule is no longer expressed through brightness or heat. It is expressed through gravity alone. Gravity is the pull that gives bodies their paths. Near the Sun, that pull is strong enough to produce short years and clear planetary rhythms. In the far frontier, the same pull acts across immense reaches of darkness. It is weaker there, but it does not disappear. Small icy bodies, dark fragments, and perhaps larger unseen worlds still move in ways that show they belong to the solar system. Their orbits remain bound to the Sun, even if one journey around it may take thousands of years, or far more. The region is quiet not because nothing happens, but because everything happens slowly. This outer frontier is not empty space in the simple sense. It contains material left over from the solar system's formation, and material that has changed little since that early time. Much of it is too small, too cold, or too dark to reveal itself easily. Ices can remain frozen for spans of time that stretch across nearly the whole history of the solar system. Some objects reflect so little sunlight that even large telescopes would struggle to notice them unless they pass through a favourable position. The farther a body lies from the Sun, the less light it receives, and the dimmer it appears. Brightness falls away so rapidly with distance that remote objects can remain hidden, simply because almost no light returns from them to Earth. This scale of this realm changes ordinary ideas of location. In the inner solar system, distance can still be imagined as a route between neighbouring planets. In the far frontier, the spaces between one orbit and another become so wide that familiar comparisons lose their force. A body can be enormously distant from Earth, yet still remain deep inside the Sun's broader sphere of influence. A world moving through this frontier would spend most of its existence in darkness so deep that the Sun would no longer dominate its sky in the way it dominates the sky of Earth. The Sun would still outshine other stars, but it would no longer feel close. It would become one brilliant point among many, marking the centre of a system that has expanded beyond ordinary intuition. Because this region is so large and so dim, knowledge of it develops indirectly. Astronomers cannot survey every part of the sky with equal depth at all times. They build understanding piece by piece, often by tracing motion, rather than by seeing structure directly. In the far solar frontier, an object may first reveal itself not through a clear image, but through a faint moving point recorded across several nights, months, or years. Even then, the path can be hard to determine. Slow motion against the background stars makes distant bodies easy to miss. A remote object may appear almost fixed, changing position only slightly while weather, daylight, moonlight, seasonal sky coverage, and instrument limits all interfere with detection. The frontier therefore remains partly known and partly inferred. Cold governs the physical character of this domain. Temperatures fall so low that volatile materials, substances that evaporate easily in warmer regions, can remain solid for immense spans of time. Frozen methane, frozen nitrogen, frozen carbon monoxide, and water ice can all endure in different combinations depending on local conditions and the history of each body. Surfaces at these distances can stay darkened by radiation and by chemical change driven by particles from space. They are ancient surfaces, altered slowly, preserving clues from the deep past. In such cold, a large world would also change its appearance. It would reflect little light unless its surface or atmosphere offered unusual brightness. The far frontier is also a boundary zone between the solar system and the larger galactic environment. The Sun does not exist in isolation. It moves through this Milky Way while nearby stars pass at great distances, and the galaxy's overall gravitational field exerts a subtle, long-term influence. In the inner regions, the planets are governed almost entirely by the Sun. Farther out, the wider setting begins to matter more. External forces remain weak, but over immense periods they can gently alter distant paths. A remote body in the Sun's domain is therefore part of two systems at once. This is what makes the outer solar frontier scientifically important. It is not only a storehouse of ancient material, it is also a record of the solar system's size, its history, and the reach of the Sun's control. Any large unseen object placed in such a region would be difficult to find for simple physical reasons. It would move slowly. It would receive very little sunlight. It would spend most of its time far from the places where telescopes most easily search. It could remain hidden not because it is impossible, but because darkness, distance, and slowness work together there. Seen this way, the farthest solar domain is less a sharp edge than a long fading territory. The known planets do not end it. They merely occupy its brighter middle. Beyond them lies a region where the Sun still rules, but softly, across enormous spans of black space. It is a realm defined by weak light, preserved cold, rare matter, and immense time. Every object found there carries unusual weight, because each one illuminates a part of a landscape that remains mostly unlit. In that still and distant frontier, the possibility of a hidden giant planet enters science not as fantasy, but as a consequence of how much of the solar system remains faint, remote, and only partly seen. Beyond the known planets and beyond the tilted path of Pluto, the solar system opens into a far larger structure that has never been photographed directly. This is the Oort cloud, a theorized outer shell of icy bodies surrounding the Sun on all sides. It is not a ring like the planetary system, and it is not a flat belt. It is understood as a vast three-dimensional envelope, almost spherical in its overall form, extending so far outward that the ordinary scale of the planets becomes almost irrelevant beside it. In this region, the Sun no longer seems like the center of a compact family of worlds. It appears instead as the dim central source of an enormous cloud of frozen remnants, spread across distances so wide that even the nearest stars begin to feel physically relevant. The Oort cloud is called theorized because it has not been seen as a complete structure. No telescope has captured it the way telescopes capture a planet, a moon, or a distant galaxy. Its existence is inferred from the paths of long-period comets. The comets that enter the inner solar system from great distances on elongated orbits, and may not return for thousands or millions of years. Their motion suggests that a huge reservoir of icy bodies surrounds the solar system far beyond the Kuiper belt. The Oort cloud is therefore known through consequence rather than direct view. It is a structure reconstructed from motion, timing, and repeated patterns in the arrival of comets. At its margin, this cloud marks one of the most remote, meaningful regions still associated with the Sun. The outermost parts are so distant that the Sun's gravity holds on only gently. Bodies there remain bound, but not tightly. Their motion is patient and vulnerable to small influences acting over immense spans of time. A passing star, even one that never comes especially close, can slightly disturb such a body's path. The broad gravitational field of the Milky Way can also exert a slow shaping effect. These influences are subtle, yet in such a loose outer domain, subtle forces can matter. Over long ages, a quiet nudge can redirect an icy object inward or alter its orbit enough to change its future entirely. This outer shell is not thought to be dense. It is enormous, but its contents are spread thinly through a volume so large that the average distance between one body and another may still be immense. Countless objects may exist there, yet the region would not resemble a crowded field. It would remain dark, sparse, and mostly empty between its pieces. The image most consistent with current understanding is not of a packed swarm, but of an immense shell of scattered icy fragments, each moving slowly through deep cold, each tracing its own long orbit around the Sun. Some may be no larger than hills or mountains. Others may be much larger. Most would be extremely difficult to detect because they reflect so little light and lie so far away. Cold defines this region more completely than almost anywhere else in the solar system. Here, the Sun offers almost no warmth in the ordinary sense. Surface temperatures on individual bodies would remain extremely low, allowing frozen materials to endure with little change. Water ice, methane ice, ammonia-rich mixtures, and other frozen compounds can survive in a preserved state for spans of time that approach the age of the solar system itself. These are ancient bodies not because they never move, but because the environment around them changes so slowly. Sunlight is faint, heating is weak, surface activity is limited. The result is a distant archive of primitive material, carried for billions of years in slow silent motion. The shape of the Oort cloud matters. Unlike the relatively flat disk of the planets and the Kuiper belt, the cloud is understood as surrounding the solar system in many directions above, below, and around the planetary plane. This makes it a different kind of region. The known planets orbit in a broad, flattened family because they formed in a rotating disk of gas and dust. The Oort cloud preserves the memory of a more complicated history. Bodies now in that spherical shell are thought to have been scattered outward during the early evolution of the giant planets and later modified by outside gravitational influences. The result is a distant population whose directions and orbital tilts are far more varied than those of the major planets. Because the Oort cloud has no direct image, its margin is known with uncertainty. Its inner and outer reaches are estimated rather than sharply measured. The outer part fades rather than ends cleanly, at some distance. The Sun's influence becomes weak enough that the gravity of other stars begins to compete more strongly. There is no bright wall, no visible boundary line, and no sudden transition in appearance. Instead, there is a gradual change from a remote solar domain to the wider gravitational setting of interstellar space. This gives the Oort cloud a special character. It is both part of the solar system and close to the point where the solar system loses exclusive control over the motion of its most distant members. For the question of a hidden giant planet, this vast shell provides essential scale. It shows how large the Sun's domain may be and how much darkness lies beyond the last known planet. A distant object does not need to lie outside the solar system to be almost impossible to see. It only needs to exist in a region where reflected light is weak, motion is slow, and the sky to be searched is immense. The Oort cloud margin is therefore important not because it is the proposed home of a hidden giant world in the simplest sense, but because it reveals the true breadth of the environment in which such a world might remain unnoticed for a very long time. In this outer shell, the solar system becomes less like a tidy set of planets and more like a fading gravitational sphere filled with preserved icy fragments. The Oort cloud margin is the grand outer backdrop of that sphere. It is dark, ancient, and only indirectly known. It reminds astronomy that the Sun's realm extends far past the orbits seen on simple diagrams, into a cold surrounding cloud that blurs the line between planetary space and the wider galaxy. Within such a setting, absence of direct sight does not mean absence of matter. It means only that the frontier is large enough, dim enough, and slow enough to keep much of itself hidden. Moving inward from the broad outer shell of the Oort cloud, the solar system does not cross a sharp boundary. There is no sudden wall of objects, no visible edge where one region stops and another begins. Instead, there is a gradual transition into a more tightly held realm, often described as the inner Oort cloud. This region remains remote beyond ordinary planetary imagination. Yet it differs from the looser outer cloud in one important way. The Sun's gravity holds its members more firmly. They still travel through deep cold and great darkness, but their paths are less easily altered by the galaxy around them. In the outermost cloud, a distant star or the slow pull of the Milky Way can reshape an orbit over immense periods of time. In the inner transition zone, those outside influences still exist, but they compete with the stronger solar grip. The result is a region that may preserve bodies more securely for long ages. A comet or icy remnant placed there remains far from the known planets, yet it is less exposed to being stripped away into interstellar space and less vulnerable to being turned inward by weak disturbances. This makes the inner Oort transition scientifically valuable. It may act as a deeper reservoir, a more protected store of ancient bodies that have stayed bound to the Sun since the early history of the solar system. This region is not observed directly. Like the rest of the Oort cloud, it is understood through theory, orbital studies, and computer models of solar system evolution. Some astronomers use the name Hill's cloud for a dense inner component, though the details remain uncertain. The exact structure, population, and extent are still not known with confidence. What is known is the logic behind its proposed existence. If the outer cloud contains icy bodies scattered long ago by the young giant planets and later modified by galactic forces, then a somewhat nearer and more tightly bound region may naturally exist inside it, holding a larger hidden population. In this view, the Oort cloud is not one simple shell, but a fading outer region built upon a deeper inner base. The physical character of that base remains quiet and cold. Sunlight is still weak beyond any familiar planetary environment. Surfaces remain frozen. Activity is slight. An object drifting there would receive too little solar energy to become active in the way a comet becomes active near the Sun. frozen gases and darker crusts could remain stable over extremely long spans of time. The bodies themselves may differ in size, shape, and composition, but the environment around them is uniformly slow. Orbits stretch across time so long that the inner-Oort transition feels less like a moving system and more like a suspended archive, held in balance by gravity. Yet balance here does not mean uniformity. The inner transition is still expected to contain a great variety of orbital shapes and inclinations. Some bodies may circle the Sun on elongated paths tilted far above or below the planetary plane. Others may remain on less extreme paths while still staying unimaginably distant. This diversity reflects the early scattering phase of the solar system. During that time, the giant planets redirected vast numbers of smaller icy bodies. Some were thrown inward, some were ejected altogether, some were sent into distant bound orbits. The inner-Oort transition may preserve the memory of that ancient sorting process more effectively than the outer cloud, because its contents are held more securely. The transition inward also changes the meaning of isolation. In the outer cloud, the solar system begins to blend with the wider stellar neighborhood. In the inner region, the Sun reasserts itself more clearly as the dominant organizer of motion. The galaxy still matters, but less decisively. A body there belongs to the Sun first and to the galactic setting second. That difference is subtle, yet it shapes the long-term fate of the region. The inner-Oort transition may therefore serve as a bridge between two regimes, one in which the solar system is only loosely bounded at its margins, and one in which solar gravity still defines the structure more strongly even at extreme distance. For comet science, this idea has practical importance. Some long-period comets that enter the inner solar system may not come directly from the farthest outer shell. They may be supplied from a nearer hidden reservoir first, then gradually passed onward into more sun-approaching orbits after long chains of disturbance. In that sense, the inner-Oort transition may function less as a visible source and more as a holding region. It stores material that can remain quiet for immense spans, then contribute to comet populations under the right dynamical conditions. This helps explain why the solar system may still possess a deep reserve of primitive icy bodies even after billions of years of change. The density of material may also differ from that of the outer shell. Although the region remains enormously sparse by ordinary standards, models often suggest that the inner Oort cloud could contain a substantial share of the mass in this distant comet reservoir. That possibility matters because it means the least visible parts of the solar system may also contain many of its most ancient small bodies. Hidden does not mean insignificant. It means the material is distributed in a region where direct observation is deeply challenging. Darkness, distance, and low motion still dominate. Even a large body there could remain beyond easy detection. The transition inward therefore reveals a subtle truth about the solar system. Its remote structure is layered not by visible walls, but by changing strength of gravitational control. Far outside, the Sun holds loosely. Slightly farther in, it holds more firmly. The inner-Oort transition belongs to this second condition. It is still a realm of deep cold, ancient ice, and near invisibility, but it is less fragile than the outer shell. It is a quieter and more protected province, one that may preserve the leftovers of planetary formation with unusual efficiency. In this hidden middle distance between the outermost cloud and the more structured regions closer to the planets, the solar system remains largely unseen but not ungoverned. The inner Oort transition is a place where ancient objects may endure in long, stable exile, carrying the record of the young solar system in frozen silence. It narrows the frontier without making it familiar. The sun is still weak there in light and warmth, yet stronger in its long command of motion. That slow strengthening of solar control marks the true inward step from the cloud's fading margin toward a more tightly bound remote interior. Inside the more weakly held reaches of the distant cloud, but still far beyond Neptune, there exists a population of icy bodies whose orbits do not fit comfortably within the familiar architecture of the major planets. These are detached objects, remote worlds of ice and rock that travel around the sun on stretched paths, while staying strangely separated from the strongest direct influence of Neptune. They are called detached because their orbits do not bring them close enough to Neptune for that planet alone to explain their present motion in a simple, ongoing way. They belong to the outer solar system, yet they seem partially set apart from its better understood gravitational patterns. A detached orbit is not detached from the sun. The sun still governs the motion completely. The detachment refers instead to a kind of dynamical distance from Neptune, the outer giant planet whose gravity shapes so much of the region beyond it. Many small outer bodies cross or approach Neptune's domain closely enough that their histories can be understood through repeated interactions with that planet. Detached objects are different. Their nearest approaches to the sun remain far enough out that Neptune cannot easily keep steering them in the ordinary way seen for many Kuiper belt objects. This gives their orbits a special importance. Each one appears to preserve evidence of a past process, a past influence, or a long-term structure not immediately visible today. These bodies are faint and hard to discover. Their surfaces reflect little light, and their great distance weakens that light even further before it reaches Earth. Most are small on planetary standards, though some are large enough to be classed as dwarf planets or candidates for that category. Even the largest remain dim because they move in an environment where sunlight is scarce. Some spend most of their immense orbital periods in regions so distant that detection becomes exceptionally difficult. Astronomers usually find such objects not because the outer solar system has become easy to observe, but because a rare object happens to lie closer to the sun along its long path, where it grows just bright enough to appear in a survey. Their orbits are often highly elongated. This means the path around the sun is not close to circular, but stretched, with one part bringing the body inward and another carrying it far outward again. For detached objects, even the inward part of that orbit may still remain at a remarkable distance from Neptune and the known planetary system. The body is never truly part of the inner solar system. It remains a citizen of the cold outer domain at all times. Such an orbit tells a story of powerful rearrangement. A body does not simply form in place on an extreme path and remain there without cause. Its current motion suggests that the young solar system or its later gravitational environment altered it in a significant way. The detached population therefore acts like a record written in orbital shape, rather than in visible geology. On Earth, a landscape can preserve the sign of flowing water or volcanic heat. In the far solar system, a path around the sun can preserve the sign of gravitational history, a stretched orbit, a high tilt, a large distance at closest approach. All of these are clues. They do not point to certainty by themselves, and they do not speak in simple language, but together they show that the outer solar system has been sculpted, not merely populated. These icy bodies are less like random leftovers and more like survivors of a long dynamical past. Some well-known detached objects have become especially important because they occupy the most extreme versions of this condition. Their paths take them so far outward, and keep them so distant even at their inward approach, that they appear to inhabit a transitional realm between the scattered outer populations and the deeper remote reservoirs of the solar system. Sedna is one of the clearest examples. Its orbit carries it to extraordinary distance, yet even its nearest approach remains far beyond Neptune. This makes it difficult to explain through ordinary present-day interaction with the known giant planets alone. Other distant objects share parts of this strange character, though each orbit differs in detail. Together they define a class of bodies that seems to require more than one simple mechanism to understand fully. The physical nature of these objects likely reflects the cold history of the outer solar system. They are thought to consist largely of mixed rock and ice, with surfaces altered over immense spans by cosmic radiation, impacts, and slow chemical change. Some may carry reddish surface colours caused by long exposure to energetic particles. Others may be darker and less reflective. Their appearance remains only partly known because they are so faint and so far away. Telescopes can often measure motion more easily than surface detail. This is why orbit becomes the main language of knowledge in this region. The body itself may remain only a tiny point of light, while its path reveals far more than its visible face. Detached orbits also remind astronomy that the boundary between categories in the outer solar system is not always clean. Some objects are clearly influenced by Neptune, some seem clearly remote from its present reach. Between these conditions lies a continuum of bodies with different histories and different degrees of separation. The detached class occupies a scientifically useful part of that continuum because it highlights where familiar gravitational explanations begin to lose completeness. The farther a body remains from Neptune at its closest approach, the stronger the sense that something in the deeper structure or earlier history of the solar system has left its mark there. This does not mean every detached orbit demands the same cause. Several processes may contribute: early migration of the giant planets, gravitational scattering during the solar system's youth, influence from the galactic environment, and rare stellar encounters have all been studied as ways to produce remote, unusual paths. Observations indicate that detached objects are not a single simple family made by one event alone. It remains uncertain how much each process contributes to the population as a whole. Yet even with that uncertainty, the detached class remains important because it gathers together the clearest examples of outer bodies whose present motion seems to preserve an incomplete explanation. In that sense, detached icy orbits form a distinct observational region of the far solar system. This region is not defined by a visible border in space, but by a shared dynamical character. Its members are bound to the sun, cold, dark, and remote. They follow long paths that seem partly insulated from the direct sculpting hand of Neptune. They preserve a state of separation that makes them unusually valuable to study. Each new discovery adds not brightness to the outer frontier, but structure. It shows that the distant solar system is not only vast and sparsely populated, it is also organized in subtle ways that can be read through motion. These icy bodies drift through darkness on timescales almost beyond human intuition, yet their orbits carry a clear message. The outer solar system contains objects whose paths are too unusual to be treated as ordinary leftovers. They are preserved traces of remote gravitational history, written in distance, tilt, and elongation. By following these detached paths carefully, astronomy studies not just isolated frozen worlds, but a hidden architecture of motion extending far beyond the last known planet, far beyond Neptune, and beyond the more familiar part of the Kuiper belt. There is a remote population of bodies that inhabit one of the least understood regions of the known solar system. These are the extreme trans-Neptunian objects, distant icy worlds, whose orbits carry them through a realm so broad and so dim that only a small fraction of its members has likely been found. The name simply means bodies that orbit beyond Neptune in especially remote and unusual ways. They belong neither to the tight, orderly family of the major planets, nor to the broad imagined shell of the outer comet cloud. They occupy an intermediate but very distant region where the Sun still governs clearly, yet where orbital shapes have become stretched, tilted, and rare. A trans-Neptunian object is any object that circles the Sun beyond Neptune. The extreme group is a narrower class within that larger population. These bodies remain so distant, even at the inward part of their orbits, that they stand apart from the more common residents of the Kuiper belt. Their paths are not gentle near circles lying close to the planetary plane. Instead, they often extend into immense ellipses, long oval paths that carry them from already remote solar distances to even more extraordinary ones. In this outer region, the ordinary visual image of the solar system as a disk of worlds becomes less useful. The system remains a flattened structure overall, but these objects move through a far more stretched and elevated orbital landscape. This region is not a belt in the simple sense of a crowded band. It is better understood as a very sparse outer domain populated by rare known objects on long individual paths. The bodies do not sit close together. Each one may be separated from the next by enormous distances, and many spend most of their orbital lives in places where they are far too faint to detect. The region appears quiet because discoveries are few, but that quietness is strongly shaped by limited visibility. A dark body in deep cold, reflecting weak sunlight across a vast gulf of space, can escape notice with ease. The known population is therefore almost certainly only a small exposed sample of a much larger hidden reality. The extreme trans-Neptunian region is defined by orbital behavior more than by direct physical appearance. Most of these bodies are visible only as points of light too small and dim for their surfaces to be resolved clearly. Telescopes measure motion across the background stars, calculate a path, and then refine that path over years of repeated observation. From that motion comes the main understanding of the region. The objects are known less as visible worlds than as long mathematical tracks through space. Their distances, tilts, and closest approaches to the Sun become the important features. In this part of the solar system, orbit is the geography. Many of these objects remain far from Neptune even when they come nearest to the Sun. That is one reason they matter. The farther an object stays from Neptune at its inward passage, the harder it becomes to explain its current path through ordinary recent interactions with that planet alone. This does not mean Neptune is irrelevant. Neptune remains one of the great sculptors of the outer solar system, and likely plays a role in the earlier histories of many distant bodies. But in the extreme trans-Neptunian region, the direct connection becomes less immediate. The objects appear to preserve orbital states that are more isolated, more ancient, or more complex than the better understood populations closer in. The timescales in this region are immense. One orbit around the Sun may take thousands or many thousands of years. During a human lifetime, an extreme trans-Neptunian object shifts only slightly along its path. Its motion is real, but patient, almost imperceptible except through careful instruments and repeated measurement. This slowness affects discovery as much as distance does. A remote object may move so gradually across the sky that it blends into the background unless a survey is designed to catch such motion. Fast nearby bodies are easier to notice. Slow distant ones can appear almost still. The outer region therefore remains undercounted not only because its objects are faint, but because their movement is subtle. The physical environment of this region is one of enduring cold. Sunlight is so weak that surfaces can remain frozen and chemically altered only by very slow processes. Water ice can stay stable. More volatile compounds may also survive, depending on the body's history and how close it ever comes to the sun. Radiation from space gradually darkens and modifies exposed material. Impacts still occur, but they are infrequent across such broad distances. The surfaces of these objects are likely old in the deepest sense, not untouched, but changed only by patient forces acting across billions of years. Their colours may range from dark neutral tones to redder shades caused by long-term irradiation of icy compounds. Some of the most famous members of this region have become important because their orbits are so extreme that they challenge simple description. Sedna remains a central example, with a path that carries it from a still very distant inward point to extraordinary remoteness. Other bodies with similarly elongated and tilted orbits expand this picture. Each new discovery helps define the region a little better, yet no single object represents it completely. The extreme trans-Neptunian domain is not one path repeated many times. It is a sparse family of remote bodies sharing a general condition of distance and orbital extremity, while differing in details that may reflect different histories. This makes the region both valuable and difficult. Valuable, because its objects preserve evidence from parts of solar system history that are less visible closer to the Sun. Difficult, because the sample remains small and strongly shaped by where astronomers have searched, when they have searched, and how sensitive their instruments have been. Some parts of the sky are observed more often than others. Some distances are easier to detect than others. A body is most likely to be found when it happens to lie in the smaller part of its orbit where it is less remote and slightly brighter. That means the known region is already filtered by chance and by method. Even with these limits, the extreme trans-Neptunian region stands out as a distinct inward step from the more remote reservoirs beyond it. Here the solar system is still very distant, still cold, and still difficult to see, but the known objects become more individually traceable. They can be named, followed, and compared. Their motions show that the outer solar system is not a blank fading edge. It contains a structured population of rare icy worlds, moving on great drawn-out paths through a dim region beyond Neptune. This region is therefore a frontier of measured motion. It is not yet the broad cloud of outer uncertainty, and it is no longer only the scattered idea of detached bodies. It is a sparse but identifiable outer population where the most remote known trans-Neptunian objects trace some of the longest and strangest paths in the solar system. In their faint movement, the distant outer domain becomes more than darkness. It becomes a mapped region, incomplete but real, where orbital extremes reveal the deep breadth and hidden complexity of the Sun's farthest known neighbourhood. Within the population of the most distant known objects beyond Neptune, astronomers begin to notice not only unusual individual orbits, but a possible pattern shared across several of them. This pattern is called orbital clustering. It refers to the idea that some of these remote icy bodies do not point in random directions around the Sun. Instead, parts of their elongated orbits appear to gather into similar orientations, as though several distant paths have been arranged by the same long-acting influence. In a region where objects are expected to be sparse and widely scattered, even a modest sign of order attracts attention. An orbit can be described in many ways, but for this pattern the most important feature is the direction in which the long ellipse is pointed. Every stretched orbit has a nearest point to the Sun, called perihelion, and a farthest point beyond it. If many distant objects formed a completely mixed population, their orbital directions might be expected to spread around the Sun without any preferred alignment. The proposed clustering suggests something different. Several extreme trans-Neptunian objects seem to bring their perihelia into a similar sector of space. Their orbital ellipses appear to lean in related directions rather than scattering evenly across all possible angles. This is important because gravity can create order over long times. In the outer solar system, direct collisions are rare and sunlight is too weak to shape motion significantly. Orbital architecture is built mainly by gravitational influence. If a group of distant objects preserves a shared directional structure over immense spans, that structure may point to a sustained gravitational cause rather than a short-lived accident. The pattern does not lie in one object alone. It appears in the collective arrangement of several remote orbits viewed together. That collective character is what gives the idea its force. The alignment is not limited only to one simple angle. In addition to the direction of perihelion, some studies point to related grouping in the orbital planes themselves. An orbital plane is the flat surface in which a body travels around the Sun. If several distant objects share similar tilts and similar directional features, the case for an organized structure becomes stronger. The picture then shifts from a handful of odd worlds to a more coherent dynamical population. The objects begin to look less like isolated exceptions and more like members of an outer system with a hidden shaping influence. This is where the idea of a distant giant planet becomes scientifically attractive. A massive unseen body on a remote orbit could, in principle, shepherd smaller objects over very long timescales. Shepherding in this context means guiding or confining orbital orientations through repeated gravitational effects. The process need not involve close encounters. A sufficiently massive object, acting across thousands or millions of years, can gradually shape the average behavior of smaller distant bodies. It can preserve some alignments, destabilize others, and create a pattern that remains visible long after the early history of the solar system has passed. The proposed orbital clustering is therefore treated as a possible footprint of hidden gravity. This does not mean the distant objects are marching in a rigid formation. Their orbits differ from one another in size, shape, and inclination. They do not lie on a single track, and they do not move as a neat geometric figure. The proposed pattern is subtler than that. It is statistical and directional. It emerges only when the known objects are considered as a group and their orbital elements are compared. A single orbit may look only unusual. A set of similarly oriented extreme orbits begins to look suggestive. That distinction matters because the Planet 9 hypothesis grows not from the existence of one remote body, but from the possibility that several remote bodies preserve the same large-scale orbital preference. The language of clustering can sound stronger than the underlying evidence if treated carelessly. In practice, astronomers are describing a tendency, not a perfectly exact arrangement. The known objects do not point in precisely the same direction. They gather within a broad sector rather than collapsing into one line. Yet the broad grouping may still matter. In dynamical systems, long-term gravitational organization often appears as a loose structure rather than a rigid one. Order in the outer solar system is expected to be imperfect because the objects are influenced over immense time by more than one process. A hidden giant planet, if it exists, would not erase all variation. It would merely make some orbital states more likely to survive than others. The pattern also matters because the extreme trans-Neptunian objects are so distant from Neptune. If their orientations remain grouped despite their remoteness and long orbital periods, then something must be maintaining or producing that organization. In the Planet 9 interpretation, The unseen planet acts as that organizing presence. Computer simulations have shown that a super-Earth mass object on a distant elongated orbit can reproduce several broad features seen in the most remote populations. This is one reason the hypothesis remains active in astronomy. It offers not only a missing object, but a mechanism capable of turning scattered anomalies into one linked outer architecture. Another reason the clustering idea carries weight is that it connects observation with prediction. Once astronomers propose that a hidden planet is shaping the orbits, the pattern ceases to be only descriptive. It becomes a tool for inference. The grouping can be used to estimate the possible mass, orbital distance, and tilt of the unseen object. In that sense, the observed arrangement of small icy worlds becomes a map drawn by gravity. The planet itself is not seen, but its possible properties are inferred from the way other bodies move. This method is cautious and indirect, yet it belongs to a long tradition in astronomy, where unseen mass is often first detected through its effects. The clustering pattern therefore occupies a special place in the search for a giant planet beyond Pluto. It is the bridge between strange distant objects and a specific physical explanation. Without such a pattern, the outer solar system would still contain many surprises, but there would be less reason to suspect one shared hidden cause. With the pattern, the idea of an unseen planet becomes more than a vague possibility. It becomes a testable gravitational hypothesis grounded in orbital structure. In this region of the solar system, where bodies are faint and direct images reveal little, motion becomes the deepest source of knowledge. The proposed clustering of extreme distant orbits is one of the clearest examples of that principle. It suggests that the far outer solar system may not be arranged at random. It may contain a large-scale directional order, subtle but persistent, written into the paths of icy worlds that take thousands of years to circle the sun. If that order is real, then the outer darkness is not empty of structure. It is being shaped, quietly and continuously, by gravity from something still unseen. In the far outer solar system, patterns are never read in a simple way. A distant object is not discovered under equal conditions everywhere in the sky, at all times of year, or at all points along its orbit. This is why the possible clustering of extreme trans-Neptunian objects leads not only to excitement, but also to caution. The same data that seem to suggest a hidden organism pattern in the sky can be treated as a true feature of nature. Astronomers must ask whether the pattern may instead reflect where telescopes looked, when they looked, and what kinds of objects they were most able to find. This problem is called observational bias. In simple terms, it means that the discovered sample of objects is not always a fair miniature of the full unseen population. Some bodies are easier to detect than others. Some parts of the sky are searched more often. Some orbital positions make an object brighter, slower, faster, or more visible against the background stars. If the outer solar system was surveyed perfectly and uniformly, the discovered objects would offer a cleaner picture of the underlying distribution. In reality, the search is uneven, built from many surveys with different depths, different seasons, different sky coverage, and different methods of follow-up. The distant sample therefore arrives already filtered before any interpretation begins. One source of bias comes from brightness. A remote icy object reflects sunlight, and that reflected light weakens sharply with distance. An object on a very elongated orbit spends most of its time in the farthest part of that orbit, where it is faintest. It becomes easier to detect only during the smaller fraction of time when it comes closer to the Sun and closer to Earth. This means discovery is strongly weighted towards certain parts of a stretched orbit. Astronomers are more likely to find an object near its inward passage than near its far outer reach. That alone can distort the apparent distribution of orbital orientations in the known sample. Another source of bias comes from where surveys point. Telescopes do not watch the whole sky equally. They avoid some regions because of bright stars, dense star fields, poor observing seasons, weather patterns, moonlight, or instrument priorities. Many surveys focus on areas near the ecliptic, the broad plane in which the planets orbit, because that is where many small solar system bodies are expected to be found. But extreme trans-Neptunian objects can appear far from that plane, depending on where they are in their orbits. If some regions are observed more deeply or more repeatedly than others, the resulting discoveries may appear to prefer certain orientations, even if the true population does not. Time adds another layer. Distant objects move slowly, so a survey must return often enough to confirm that a faint point of light is not a star or image defect. Some objects are lost because they are not followed long enough. Others are found in one season but cannot be recovered in another. Long-term orbit quality depends on patient tracking. A body with a poorly determined orbit may not contribute reliably to statistical studies of clustering. This means the sample is shaped not only by who is found first, but also by who remains well measured over time. Discovery and retention both influence the final set of objects used in dynamical arguments. Small numbers deepen the uncertainty. The most extreme distant bodies are rare discoveries, and the sample that matters most to the Planet 9 debate is still modest. When a population is represented by only a limited number of objects, chance can imitate structure. A few unusual discoveries can create the appearance of order, even when the underlying distribution is broader or more random. This does not mean the clustering is false. It means that confidence must be earned carefully. In a small sample, each new object carries unusual statistical weight. One discovery can strengthen a pattern, weaken it, or complicate it enough to force a new interpretation. This is why the debate remains active. Some researchers argue that once discovery biases are modelled properly, the apparent alignment of distant orbits becomes less compelling, or may even be consistent with a population that is not truly clustered. Others argue that the pattern survives those corrections and still points toward a real gravitational cause. The disagreement is not simply between belief and disbelief. It is about methodology. It concerns how to reconstruct an unseen population from an uneven set of detections and how much confidence can be placed in the resulting pattern. The outer solar system is not handing over a clean census. It is offering a sparse set of faint-moving targets discovered under imperfect conditions. Survey design has become central because of this problem. Some projects are built specifically to measure their own biases so that detected objects can be compared more fairly with models. This is an important advance. It changes the question from whether a pattern looks convincing by eye to whether it remains convincing after the conditions of discovery are formally accounted for. In this sense, the Planet 9 debate has helped sharpen outer solar system astronomy more broadly. It has pushed the field toward more careful treatment of selection effects, sample completeness, and the difference between what exists and what happens to be seen. Bias does not only affect direction in the sky, it can also influence which perihelion distances, inclinations, and sizes are represented in the discovered sample. A survey may be more efficient at finding some kinds of distant objects than others, and those preferences can feed directly into theories about outer solar system structure. The result is a delicate situation. The very objects most useful for testing the hidden planet idea are also among the hardest to detect in an unbiased way. Their rarity and faintness make them scientifically precious, but also statistically fragile. At the same time, bias is not a universal dismissal. To say that survey effects matter is not to say that every apparent pattern is an illusion. It means only that a pattern must survive a more difficult test before it is accepted as physical. In astronomy, this is a familiar discipline. Many discoveries begin as suggestive arrangements in incomplete data. Some fade when better surveys arrive. Others grow stronger. The outer solar system is passing through exactly that process. Its distant objects are being transformed from scattered curiosities into a population that can be analysed with increasing care. This makes the region of debate itself a meaningful layer of understanding. It is not merely an argument around the science. It is part of the science. In this layer, astronomers study not only distant worlds, but the limits of their own view. They examine how darkness, slow motion, uneven sky coverage, and small samples can shape the appearance of order. The question is no longer only whether the outer orbits are clustered. It is whether the observed clustering remains after human seeing has been measured and corrected as carefully as possible. In that careful tension between possible signal and possible bias, the far solar system becomes more rigorous, not less mysterious. The debate does not weaken the subject, it gives it discipline. It keeps the hidden planet theoretical while allowing the evidence to be tested against the deepest practical limits of observation. Here, before any unseen world can be accepted as real, astronomy must first learn how much of the apparent structure belongs to the sky itself, and how much belongs to the way the sky has been searched. If a giant planet truly moves beyond Pluto, and beyond the better-known part of the Kuiper belt, then its great protection is not only darkness, but location. The sky is vast, and a distant body does not occupy it in the way a nearby planet does. It does not shine brightly enough to announce itself. It does not race across the stars. It lingers in a huge search region, moving so slowly and reflecting so little sunlight that it can remain hidden inside ordinary sky images unless astronomers know where and how to look. The search region is therefore not one narrow point in space. It is a broad and shifting portion of the outer solar system projected across a large part of the sky. The difficulty begins with simple geometry. A body orbiting far from the Sun travels more slowly than a body orbiting close in. That is a basic consequence of orbital motion under gravity. The farther the path, the longer the journey, and the slower the pace. A proposed giant planet at extreme distance would therefore drift against the background stars at a rate so small that, from night to night, it could appear almost fixed. Many search programs for smaller nearby solar system objects are designed to find motion that is easier to notice. A hidden giant in the far dark would demand more patient methods. It might reveal itself only after images taken weeks, months, or even years apart are compared carefully. Its faintness adds a second difficulty. A distant planet is seen mainly through reflected sunlight, unless its own internal heat contributes enough at longer wavelengths to be measured. But sunlight weakens greatly with distance from the Sun, and the reflected light then weakens again as it travels back outward toward Earth. This double loss makes remote bodies dim very quickly. A planet that might be large in physical size can still appear as a faint point if it lies far enough away. In practice, that means the likely search region includes many places where ordinary sky surveys are simply not deep enough to pick out such an object reliably. The region of sky to be searched is also shaped by orbital statistics. If a distant planet follows a stretched path around the Sun, it would not spend equal time in all parts of that path. Objects in elongated orbits move more quickly when nearer the Sun and more slowly when farther away. Because of that, such a planet would spend most of its time near the far part of its orbit, where it is most distant, slowest, and hardest to detect. This strongly affects the search region. Astronomers are not equally likely to find the planet anywhere along its path. The most probable location, simply by time spent, may also be the least favourable for direct discovery. This turns the search region into a paradoxical landscape. The areas where a hidden planet is most likely to be found in principle are not always the areas where it is easiest to see in practice. Closer portions of a distant orbit offer more reflected light and slightly faster motion, which help detection, but the planet would pass through those easier positions for a smaller share of its long year. Farther portions offer more time, but less light and less motion. A realistic search must therefore balance probability of presence against probability of visibility. It is not enough to ask where the planet could be. It is necessary to ask where it would be both present and detectable. Sky location matters in another way as well. Some parts of the sky are easier to survey than others. Dense star fields near the plane of the Milky Way can hide faint moving points among countless background sources. Bright stars can produce scattered light and image defects. Seasonal weather limits observing from many ground-based telescopes. Some regions are visible only during certain months or only from certain latitudes on Earth. The search region for a hidden planet is therefore filtered through the practical limitations of astronomy. Even a strong telescope cannot search everywhere equally well. A candidate world may remain concealed not because it is outside reach in an absolute sense, but because it lies in a crowded or poorly timed part of the sky. The search also depends on wavelength. Visible light surveys are useful because they can scan broad areas of sky and detect faint reflected sunlight. Infrared searches offer a different advantage. A remote giant planet may still retain some internal heat from its formation and slow cooling, especially if it is more like an ice giant than a rocky body. That heat would be weak, but it could make the planet slightly more noticeable at longer wavelengths than it would be in visible light alone. This does not remove the difficulty, it only changes the search region by adding another way to define it. Some areas of sky may be promising not because reflected sunlight is strongest there, but because thermal emission might be easier to separate from the background. As the search region is narrowed, astronomers combine several kinds of information. The distant icy objects already known provide indirect hints by indicating where a hidden planet might best fit the outer orbital architecture. Survey limits show where previous searches have already ruled out brighter possibilities. Sky conditions determine where new observations can be made efficiently. The result is not a single answer, but a map of probabilities, exclusions, and remaining open territory. Some parts of the sky become less likely because deep surveys have already searched them well enough that a sufficiently bright planet should have appeared. Other parts remain less constrained and therefore more interesting. Even so, the search region never becomes a simple target circle. Uncertainty in the planet's possible orbit spreads the allowed positions widely. Small changes in orbital assumptions can shift the best candidate areas across large arcs of sky. This is one reason the planet has not simply been found or dismissed. The search does not resemble pointing one telescope at one predicted spot and waiting. It resembles gradually reducing a vast outer domain through repeated observation, modelling, and elimination. Each non-detection matters, but it must be interpreted in terms of what that particular survey could actually have seen. The search region is therefore a scientific territory defined by darkness, slowness, and incomplete coverage. It lies not only in the outer solar system but also in the outer limits of detection itself. A hidden planet could remain unseen there because it spends long ages in the dimmest part of its path, in a region of sky that is broad, seasonally limited, or crowded with background stars. Astronomy responds by turning the sky into a structured field of likelihood rather than a blank unknown. It studies where the planet would most probably linger, where telescopes are most sensitive, and where both conditions overlap. In this way, the search region becomes more than a place. It becomes the practical face of the Planet 9 hypothesis. It is the area where theory meets the real sky. Within that wide and faint territory, astronomers continue to look for a slow-moving point of light that may exist, may remain hidden, and may reveal itself only when patience, probability, and improved observation finally converge. If a giant planet is truly hiding beyond Pluto, then its defining feature is not only its distance, but the shape of its path around the Sun. The proposed orbit is not imagined as a near circle like those of the major planets in their simplest textbook form. It is usually described as a long ellipse, a stretched orbital path that carries the planet through an enormous range of solar distances. In that picture, the planet does not remain at one steady outer radius. It travels inward and outward across the deep frontier of the solar system, always remote, always faint, but not always equally far from the Sun. An ellipse is an oval path with two unequal ends. For a planet, this means there is a nearer part of the orbit and a farther part. The nearer point is called perihelion, the point of closest approach to the Sun. The farther point is called aphelion, the most distant reach of the path. In the case of the proposed hidden planet, both of these points would still lie far beyond Neptune. Even the nearer part of the orbit would remain in a region of deep, cold, and weak sunlight. The farther part would reach into a realm where the Sun's light becomes so thin that the planet could spend most of its long existence almost entirely concealed from ordinary view. This elongated shape matters because it helps explain both the proposed influence of the planet and the difficulty of finding it. A nearly circular distant planet would produce one kind of long-term gravitational structure. A stretched orbit can produce another. The changing distance between the hidden planet and the smaller distant bodies beyond Neptune allows its gravitational effect to vary over time and location. At some phases of its long cycle, it would move through regions where its influence on certain remote populations becomes more dynamically important. At others, it would retreat into such distance that direct detection becomes even more difficult, while its long-term orbital imprint may still remain. Models that attempt to reproduce the unusual orbits of extreme trans-Neptunian objects often place the hidden planet on a path measuring several hundred astronomical units in its average scale. Some versions place its nearest approach at several hundred astronomical units, and its farthest distance at many hundreds more. These are not measured facts, because the planet itself has not been seen. They are dynamical estimates, inferred from the orbital architecture of smaller bodies and from computer simulations that try to match that architecture. Observations indicate a distant elongated orbit is one of the more effective ways to explain the patterns that have motivated the hypothesis. It remains uncertain exactly how stretched that orbit would be, or whether the true solution, if any, lies within the currently favoured range. The orbit is also thought to be inclined. Inclination means the path is tilted relative to the broad plane in which the major planets travel around the Sun. The known planets occupy a system that is mostly flat, a legacy of their formation in a rotating disk of gas and dust. A hidden planet beyond Pluto is not usually placed directly within that same flat plane. Instead, many models give it a moderate tilt, enough to lift part of its orbit above and below the main planetary layer. This helps the hypothesis account not only for certain alignments among distant objects, but also for some unusual high-inclination bodies that appear difficult to explain through Neptune alone. That tilt has an important consequence for how the orbit occupies space. The hidden planet would not simply move farther out along the same broad track as the known planets. It would weave through a quieter, higher, more solitary route, spending part of its vast journey above the ordinary planetary plane and part below it. In this way, the orbit becomes not just long but spatially separate. It carves a remote path through a three-dimensional outer solar system, reinforcing the idea that the far frontier is not a single flat sheet of debris but a layered and structured gravitational domain. Time is the deepest expression of such an orbit. A planet moving at these distances would not complete a year in decades or centuries. Its cycle around the Sun would likely take many thousands of years. Some estimates place that orbital period on the order of 10,000 or more years, depending on the exact size and shape of the proposed path. This means that throughout recorded human history, the planet would have shifted through only a tiny fraction of one revolution. Its motion would be real, but it would unfold on timescales far longer than civilization itself. Such slowness is one reason it can remain hidden inside existing astronomical images. A body so distant may move too gradually to stand out unless observers compare carefully spaced observations with great patience. The long ellipse also means the planet would spend unequal amounts of time in different parts of its orbit. In celestial mechanics, a planet moves faster when it is closer to the Sun and slower when it is farther away. For a strongly elongated orbit, that difference becomes pronounced. The proposed giant would pass relatively more quickly through the inward part of its path, where it would be somewhat brighter and easier to find, then linger for much longer in the outer part, where it would be dimmest and hardest to detect. This is why its orbit is closely tied to the search problem. The shape of the path determines where the planet is most likely to be at any given time, and that most likely region may also be the least favourable for discovery. The proposed orbit is not only a matter of size and tilt, its orientation in space also matters. If the Planet 9 interpretation is correct, the direction in which the orbit points may help explain the grouped orientations of certain extreme distant objects. The hidden planet would not simply add mass to the outer solar system, it would add a specific geometry, a preferred direction and tilt that smaller bodies respond to over immense spans of time. In this sense, the orbit is the real engine of the hypothesis. Without the right path, the planet would be only another distant world. With the right path, it becomes a possible organizer of the outer system's most unusual motions, yet caution remains essential. The orbit described in the literature is a family of possibilities, not a single measured track. Different researchers obtain somewhat different preferred solutions depending on which distant objects are included, how biases are modelled, and which dynamical features they try to reproduce. Some solutions place the planet closer, some farther, some more tilted, some less. The broad image remains consistent, a distant, elongated, inclined orbit far beyond Neptune. The details remain open. This is the natural condition of a planet inferred through gravitational clues rather than direct sight. In the end, the possible planetary orbit is best understood as a long, cold, tilted ellipse drawn through the outer darkness of the sun's domain. It is a path measured not by direct images of a world crossing the sky, but by the quiet arrangement of smaller bodies whose own remote motions hint at an unseen guide. If such a planet exists, its orbit would be one of the grandest in the solar system, not because it is dramatic in a visible sense, but because it is vast, patient, and almost entirely hidden within time. Once the possible orbit has been imagined, the next inward layer of the hidden planet idea concerns the body itself as a source of gravity. A planet far beyond Pluto cannot be weighed on a scale or measured directly through its visible disk, because no such object has yet been seen. Its mass and size are therefore inferred indirectly. Astronomers ask what kind of body would be strong enough to shape the distant icy orbits under discussion, yet faint and remote enough to remain undetected. In this region of the hypothesis, the proposed planet becomes less a moving path and more a physical world with bulk, gravity, and dimensions that can be estimated from its effects. Mass is the most important of these properties. In astronomy, mass determines how strongly an object pulls on other bodies and how deeply it influences the structure around it. A more massive planet can disturb or guide distant small objects more effectively over long timescales. A less massive one may fail to preserve the broad orbital patterns that gave rise to the hypothesis in the first place. This is why the hidden world is usually not imagined as a body comparable to Pluto or even to Earth in a simple one-to-one way. The proposed object is commonly treated as a larger planet, one with enough gravitational authority to organize the outer system across immense spans of time. Many dynamical studies have suggested a mass greater than Earth's, often within the range of a super-Earth or a small ice giant. A super-Earth is a planet more massive than Earth, but still far below the mass of Uranus or Neptune. In different modelling efforts, the favoured value has varied, but a common broad range places the hidden planet at several times the mass of Earth. Some estimates have centred near 5 Earth masses, while others have allowed values closer to 10 Earth masses. These numbers are not direct measurements, they are best understood as working solutions, masses that make the long-term orbital architecture more plausible in simulations. Observations indicate that a body much smaller than this may struggle to create the proposed patterns, while a body much larger could produce stronger effects than those actually seen. This inferred mass gives the hidden planet a distinct place in the family of planetary bodies. It would not be a giant planet in the same class as Jupiter or Saturn, whose masses dominate broad regions of the solar system, nor would it be merely a large dwarf planet. It would occupy an intermediate category, larger than the terrestrial planets in mass except Earth, yet smaller than the familiar outer giants. In that sense, it would resemble a kind of planet that appears common around other stars but is missing from the known planets of this solar system. Many extrasolar systems contain worlds between Earth and Neptune in mass and size. The possible outer hidden planet is intriguing, partly because it would fill that missing category here. Size follows from mass, but not in a simple way. A planet's radius depends not only on how much material it contains, but also on what that material is and how it is arranged. A dense rocky body and a less dense ice-rich or gas-rich body can share the same mass while differing in physical diameter. Because the composition of the hidden planet remains unknown, its size must be estimated more cautiously than its gravitational strength. If it contains a substantial fraction of ices and light gases, it could be appreciably larger than Earth in diameter while still remaining far smaller than Neptune. If it is denser and more rock-rich, it could be somewhat more compact. Most plausible versions of the planet suggest a world with a radius larger than Earth's, perhaps several times Earth's radius, though the exact value remains uncertain. Density becomes the silent link between these unknowns. Density is the amount of mass packed into a given volume. It helps determine whether a planet is more like a scaled-up rocky world, a deep, icy planet, or a smaller cousin of the known ice giants. Yet density cannot be observed here because neither mass nor radius has been measured directly. It must be inferred from formation theory and from comparison with planets found elsewhere in the galaxy. This is why current descriptions of the hidden planet often remain deliberately broad. It is treated not as a known object with fixed dimensions, but as a likely class of object whose mass is better constrained than its radius, and whose radius is better constrained than its internal makeup. The body's gravitational reach would extend far beyond its physical size. Even a planet only a few times wider than Earth could influence surrounding orbital space across immense distances if it carried several Earth masses of matter. In the outer solar system, where the background environment is sparse and orbital times are long, a moderate planetary mass can still matter greatly. This is one reason the hidden planet does not need to be enormous in the sense of Jupiter. Distance and time magnify subtle gravitational work. Over millions of years, a planet of several Earth masses can reshape the survivability and orientation of smaller distant bodies without ever revealing itself through bright reflected light or easy telescopic visibility. There are also upper and lower limits to what astronomers consider plausible. If the hidden planet were too low in mass, it would fail to maintain the proposed orbital organization. The distant icy bodies would drift into a more random configuration, or would require another explanation. If the planet were too high in mass, it could produce additional effects that might already have been noticed, either in the motions of known bodies or in wide-area sky surveys sensitive enough to find a brighter or warmer object. This places the hypothesis in a narrow but still open zone of possibility. The planet must be heavy enough to matter, light enough to remain subtle, and distant enough to stay hidden. Mass and size estimates are also linked to origin. A planet of several Earth masses is not a trivial leftover. It would represent a serious product of planetary formation, either built in the young solar system and later displaced outward, or perhaps captured under unusual conditions early in solar history. A body of that scale would carry enough material to have evolved as a true planet, not merely as a large minor body. This makes the inferred mass important not only for current dynamics, but for the deeper history of the solar system. The planet, if real, would not be a small oddity at the margin. It would be a major member of the planetary family hidden only by remoteness. Even so, all such estimates remain conditional. They depend on the assumption that the observed distant orbital structure truly requires a hidden planet. If the clustering weakens under better surveys or proves to arise from bias, then the inferred mass and size lose their physical anchor. They are not free-floating facts. They are consequences of a hypothesis under test. That is why responsible descriptions remain careful. Observations indicate that a planet of several Earth masses could explain some features of the distant population. It remains uncertain whether such a planet exists, and therefore uncertain whether any inferred size belongs to a real world or only to a useful model. Within that uncertainty, the hidden planet takes on a provisional bodily form. It is imagined as a remote world heavier than Earth, lighter than Neptune, substantial enough to shape the outer solar system, yet still small enough in brightness and scale to evade direct discovery at great distance. Its mass is the main source of its proposed power. Its size is the visible expression that still remains unknown. Together they define the hidden body not as a fantasy of limitless proportions, but as a restrained and physically plausible planet, one whose most important property is not how large it looks, but how much unseen gravity it carries through the dark beyond Pluto. At this stage of the hidden planet idea, the world beyond Pluto is no longer considered mainly as a path or a source of gravity. It is considered as something that might, under the right conditions, be seen. That possibility begins with light and heat. A distant planet does not present itself to telescopes in the way a nearby bright planet does. It does not fill the eyepiece with a visible disk. It does not blaze across the sky. It appears, if it appears at all, as a dim point, carrying only a small amount of reflected sunlight and perhaps a faint trace of warmth from within. Its appearance would be shaped by distance before anything else. Reflected sunlight is the first and simplest source of visibility. The sun shines on the planet, and the planet sends a fraction of that light back into space. That fraction depends on surface or cloud brightness, often described by the term albedo. Albedo means reflectivity, the share of incoming light that is reflected rather than absorbed. A bright icy surface has a higher albedo than a dark rocky or radiation-darkened one. A planet with pale clouds could also reflect more light than a bare, darker surface. Yet even a fairly reflective world grows faint at great distance, because the sunlight reaching it is already weak, and the reflected light must then travel across another vast span to reach Earth. This double weakening is severe. If the planet lies several hundred astronomical units from the Sun, the amount of sunlight falling on it is only a tiny fraction of what Earth receives. The reflected signal is weaker still by the time it arrives at a telescope. A large body can therefore remain visually inconspicuous simply because almost no light is available to reveal it. This is one reason the hidden planet is not imagined as glowing brightly in darkness. It would be faint in visible light, even if it were substantial in size. Its remoteness would dominate its appearance more strongly than its physical diameter. Color would likely be subdued. In the outer solar system, sunlight is weak and surfaces are shaped by deep cold, irradiation, and long chemical change. A distant planet with a substantial atmosphere might appear bluish, greyish, or softly muted depending on the gases and hazes present. A darker and less reflective world could appear more neutral or reddish in its light signature if irradiated compounds influence the upper visible layers. But from Earth, none of this would present itself as a richly detailed globe. The planet would probably be unresolved, meaning it would remain too small in the sky for its disk to be clearly separated by most observations. Its colour would be inferred from delicate measurements rather than seen directly as a miniature world with visible bands and features. Heat offers a second path to detection. A planet is not only a mirror for sunlight. It may also release internal heat left over from its formation and from the slow compression and cooling of its interior over time. In the far outer solar system, this can matter because reflected sunlight becomes so weak that even a small amount of internal warmth may improve visibility at longer wavelengths. This warmth would not make the planet hot in any ordinary sense. It would remain a very cold world, but in infrared light, which traces thermal emission. The planet might stand out a little more than it does in visible light. It would not shine like a star. It would simply be less dark than a body with no retained internal heat at all. The balance between reflected light and internal heat depends strongly on the planet's composition and history. A smaller rocky world tends to cool more thoroughly over time than a larger body wrapped in deeper volatile layers. A planet of several Earth masses, especially one with an ice-rich or gas-bearing structure, may hold on to internal heat more effectively. That possibility is one reason astronomers consider infrared surveys alongside visible light searches. The hidden planet may be too dim to notice easily by reflected sunlight alone, while still carrying enough gentle thermal emission to become more detectable at longer wavelengths. Even so, detectability through heat remains limited. Distance weakens every signal, and the outer sky contains many sources that complicate the search. Background galaxies, cold dust, image noise, and the sheer breadth of the region all make identification difficult. A remote planet would not stand out as an obviously warm object. It would remain a faint candidate among many faint points. Its heat would help only modestly. The world's basic appearance would still be one of quiet obscurity, a body revealing itself only through careful analysis rather than visual drama. If such a planet possesses an atmosphere, that atmosphere would influence appearance even before its deeper structure is known. High clouds or upper hazes could increase reflectivity and soften the visible character of the world. Seasonal changes driven by its slow changing distance from the sun might alter condensation of gases in the outermost layers, affecting brightness over very long timescales. But these changes would unfold so slowly, and the planet would appear so tiny, that the immediate visual impression from Earth would remain minimal. Telescopes would most likely record a point source, not a richly textured planet. The appearance of the world would therefore be statistical and instrumental before it became pictorial. This is a useful reminder of how astronomy works at the edge of visibility. A planet can have real colour, weather, reflectivity, and heat, while still appearing to observers as almost nothing. The hidden world beyond Pluto, if it exists, would likely occupy exactly that condition. It would be physically complex and visually modest. Its observable identity would come from brightness measurements, motion across repeated images, and perhaps faint thermal clues. It would not first enter science as a beautiful globe. It would enter as a dim object behaving like a planet. Its brightness would also vary with position along its orbit. When somewhat nearer the sun, it would receive more light and reflect more of it. It would also be slightly closer to Earth on average, improving visibility. When farther out, both effects would reverse. Because the proposed orbit is elongated, the difference between brighter and dimmer phases could be meaningful. Yet the brighter phase would still not make the planet easy to see. It would only make it less difficult. The farther phase would be especially challenging, perhaps leaving the body below the practical reach of many surveys. This changing brightness is one reason the hidden planet may remain undiscovered, even if its general class and size are physically plausible. The apparent size of the world in the sky would remain extremely small. Even a planet several times Earth's radius would subtend a tiny angle at such distance. Most observations would treat it as a point, meaning that all information about its character would have to be extracted from the intensity and distribution of light, rather than from a visibly resolved disk. This keeps the planet ghost-like in observational terms. It would be present, but scarcely shaped. Seen from Earth, it would not resemble Neptune drifting at the edge of the solar system. It would resemble a faint and patient signal hiding among stars. So the likely appearance of the hidden planet is one of restraint. It would be dim in visible light, modestly helped by internal heat in infrared light, and difficult to resolve as a true disk. Its colour would be muted, its brightness uncertain, and its detectability strongly controlled by orbital position. In physical reality, it could be a substantial world, cold but active in slow planetary ways. In observational reality, it would remain almost minimal, a tiny point in the outer darkness whose faint light and weaker warmth are just enough to keep the search alive. If the hidden planet beyond Pluto is a true world of several Earth masses and has managed to retain light gases since its formation, then its outermost visible layer would likely be an atmosphere. This atmosphere would not resemble the warm, sunlit skies familiar from the inner solar system. It would exist in a realm where sunlight is thin, seasons unfold across thousands of years, and cold shapes nearly every outward feature. The upper atmosphere would be the first planetary layer to meet space, the first to absorb the weak outer light of the sun, and the first to reveal how a distant planet lives under such faint illumination. At these enormous distances, the sun would no longer act as a strong heating source. It would still provide light, but only in a greatly diminished form. Daylight at the hidden planet, if it exists, would be far weaker than daylight at Earth, and even weaker than the weak illumination that reaches Neptune. The upper atmosphere would therefore receive only a small amount of solar energy. This matters because the outermost gases of a planet respond directly to incoming light. Where sunlight is strong, upper layers can warm, expand, and drive active chemistry. Where sunlight is weak, those processes become quieter and slower. The atmosphere beyond Pluto would still be dynamic, but its dynamics would unfold in a subdued and patient way. The likely composition of such an outer atmosphere depends on the planet's origin and mass. If it is more like a scaled-down ice giant, the upper layers may be dominated by hydrogen and helium, with smaller amounts of methane and perhaps trace gases in even lower abundance. Hydrogen is the lightest element and a common atmospheric constituent in large outer planets. Helium is similarly light and chemically calm. Methane matters because even in small amounts it can strongly affect the way a distant planet interacts with light. Methane absorbs red wavelengths efficiently, which can give an atmosphere a cooler bluish appearance when enough sunlight is available to reveal that effect, yet at the probable distance of the hidden planet. Any colour would be muted by darkness and by the planet's tiny apparent size in the sky. The upper atmosphere would likely be rarefied compared with the denser layers lower down. It would not be empty, but its gases would be spread more thinly as pressure falls outward towards space. This thinning changes the behaviour of light and heat. In the highest layers, particles are farther apart, collisions are less frequent, and energy moves through the gas in a more delicate balance. Weak sunlight can still break apart some molecules, especially in the highest exposed levels. That process is called photochemistry, the chemical transformation of gases by light. Even under weak solar conditions, photochemistry may still slowly alter methane and related compounds, creating more complex hydrocarbons and possibly fine hazes suspended in the upper atmosphere. Such hazes could matter more than their small mass suggests. A thin layer of suspended particles can change how a planet reflects light, softening or dulling the visible signal that reaches distant telescopes. On outer planets already known, hazes and high clouds help shape overall colour and brightness. On a hidden planet, they may do the same, perhaps even more subtly because the available sunlight is so limited. If the upper atmosphere contains methane and enough ultraviolet light reaches it, chemical byproducts could accumulate in the high cold air and settle slowly downward. The result might be a muted outer veil rather than a sharply clear atmosphere. Temperature in the upper layers would be extremely low. That statement does not mean every part of the atmosphere would be equally cold. Atmospheric temperatures vary with altitude depending on how gases absorb sunlight emit heat, and circulate vertically and horizontally. But the general setting would be severe cold. The weak solar input would favor low equilibrium temperatures, meaning the planet's upper atmosphere would tend toward a very cold average state unless internal heat from the planet below altered the balance. Even then, the highest exposed layers would still belong to a cold regime compared with the atmospheres of the inner planets. This cold would influence chemistry, cloud formation, and the stability of volatile compounds. One important consequence of such low temperatures is condensation. A gas condenses when it cools enough to form droplets, crystals, or particles. In the outer solar system, methane can condense under the right conditions, and other compounds may also do so depending on pressure and temperature. In the hidden planet's upper atmosphere, some constituents may exist near their condensation thresholds over long spans of orbital time. Because the proposed orbit is elongated, the amount of sunlight reaching the planet could change significantly over its immense year. That change would be slow, but real. As the planet moves inward or outward across its long ellipse, the thermal structure of the high atmosphere may gradually adjust, allowing some hazes or condensates to become more or less prominent over thousands of years. The upper atmosphere would also define how the planet meets the solar wind. The solar wind is the outward flow of charged particles from the Sun. By the time it reaches the far outer solar system, it is weaker than it is near Earth, but it still exists. If the hidden planet has a magnetic field, the upper atmosphere may interact with that field and with incoming charged particles in ways that shape auroral activity or high-altitude energy deposition. If the planet lacks a strong magnetic field, its upper gases may interact more directly with space plasma. In either case, the boundary between atmosphere and space would not be a simple still surface. It would be a zone of slow exchange, where sunlight, particles, and planetary gravity all meet. Escape of gas from the upper atmosphere would likely be limited if the planet is truly several Earth masses. Stronger gravity helps a planet retain light gases over long time scales. This is one reason a hidden planet of modest planetary scale could still preserve a hydrogen-rich outer envelope in the deep cold beyond Pluto. Weak solar heating would also reduce some escape processes compared with what might happen closer to the Sun. The upper atmosphere would therefore be expected to persist rather than evaporate away easily. It would remain thin at its highest edge, but not fragile in an immediate sense. It would be a long-lived planetary skin, stretched over immense time. Wind in the upper atmosphere would probably exist, though not in a way visible from Earth as obvious weather patterns. Planets with atmospheres rarely remain motionless. Differences in temperature, rotation, and energy transport generate circulation. On a hidden world, those winds might be influenced less by direct sunlight than by the planet's rotation and internal heat leaking upward into the higher air. Yet the uppermost levels would still reflect the cold geometry of outer sunlight. Day and night contrasts may be weak if circulation is efficient, but seasonal contrasts across the long orbit could matter over very long periods. The atmosphere would not be static. It would simply change on timescales so slow that the planet's life in air would seem almost geological. So the upper atmosphere of the giant planet that may be hiding beyond Pluto would be a cold, thin, chemically quiet but not lifeless layer, shaped by faint sunlight, possible methane chemistry, high-altitude hazes, and the long restraint of distance. It would be the planet's soft outer face, meeting space without brightness, holding its gases under deep cold, and carrying the first visible signs of a world that remains almost entirely unseen from Earth. Beneath the cold outermost air of the hidden planet, The atmosphere would likely deepen into a far denser and more substantial gaseous envelope. In this region, space no longer feels close. The thin exposed upper air gives way to layers where pressure rises steadily. Gases crowd more closely together, and the planet begins to resemble the familiar ice giants in a broader physical sense. This deeper atmosphere would still belong to a world beyond Pluto, still shaped by weak sunlight and extreme distance, but it would no longer be defined mainly by faint external illumination. Here, the important forces would be pressure, composition, circulation, cloud formation, and the slow upward leakage of internal heat. Pressure is the first great change. In an atmosphere, pressure increases with depth, because each lower layer must support the weight of all the gas above it. On a hidden planet of several Earth masses, this increase could become significant over a relatively modest vertical distance compared with the scale of the whole atmosphere. The deeper one descends, the more tightly packed the gas becomes. Molecules collide more often. Heat is transferred more effectively. The behavior of the atmosphere becomes less like a rarefied outer skin and more like a true planetary fluid. Even without any solid surface nearby, the atmosphere would become thick enough to create a meaningful internal weather environment. The main gases in this deeper region would likely still be hydrogen and helium if the planet formed and evolved as a smaller relative of Uranus or Neptune. These light elements would dominate by abundance, but they would not be alone. Mixed within them would be smaller amounts of methane, ammonia, water-related vapor at suitable depths, and other volatile substances depending on the planet's exact origin. In the deeper gaseous layers, these minor components become especially important because they can condense into clouds when pressure and temperature cross the right thresholds. A cloud in this sense is a layer where gas cools or compresses into suspended droplets or crystals. The deeper atmosphere of a cold, distant planet may therefore contain multiple cloud decks stacked at different depths. Methane is one likely cloud-forming constituent in upper parts of the thicker atmosphere. Farther down, if conditions permit, other materials could condense in turn. The sequence depends on the planet's temperature profile, meaning how temperature changes with depth. In a cold outer world that still releases some internal heat, temperature may rise again deeper down even while pressure increases. This creates zones where certain gases are stable as vapor above, then form clouds below, and later become gaseous again at still greater depth under warmer conditions. Such transitions are common in the atmospheres of giant planets. The hidden world may therefore possess a layered cloud structure, with each layer marking a boundary between one physical state and another. These clouds would not resemble clouds on Earth in appearance or behavior, though the basic principle is the same. Earthly clouds form mainly from water in a relatively thin atmosphere under strong solar heating. On a distant planet beyond Pluto, clouds would form from very different materials in an atmosphere far thicker and colder, with weaker sunlight and more important internal energy. Their colors, opacity, height, and distribution would depend on chemistry and circulation, rather than any familiar sky-like scene. From far away, such clouds might contribute to the overall brightness and muted color of the planet. Within the atmosphere itself, they would be part of a slow, layered weather system governed by planetary scale motion. Circulation in the deeper atmosphere would probably be more vigorous than the weak sunlight alone might suggest. Giant and ice giant planets do not depend only on sunlight to drive atmospheric motion. Internal heat can rise from lower layers and help power vertical mixing, winds, and broad circulation cells. If the hidden planet retains even a modest internal heat flow, that warmth could move upward into the deeper atmosphere and interact with rotation to produce bands, jets, or long-lived flow structures. Rotation matters because a spinning planet tends to organize moving gases into east-west patterns, rather than allowing them to drift freely in all directions. The result could be an atmosphere structured into broad zones of faster and slower wind, even though the world itself remains dim and distant. The pace of that weather would likely be slow in outward appearance but active in physical terms. On a far cold planet, visible change might not be dramatic from the perspective of a distant telescope, yet the atmosphere could still be constantly moving, gas rising in warmer regions, sinking in cooler ones, forming clouds, dissolving them, and carrying heat from one depth to another would all contribute to a living gaseous system. Storms may also be possible, particularly if condensation of volatile compounds releases latent heat. Latent heat is energy released when a gas condenses into liquid droplets or solid particles. This released energy can strengthen upward motion and help build local disturbances. Even on a cold world, clouds can therefore support episodic atmospheric activity. Because the planet's orbit is likely elongated, the deeper atmosphere may also experience extremely long seasonal adjustment. As the planet moves gradually closer to or farther from the Sun over thousands of years, the weak external heating at the top of the atmosphere would change. Those small changes could slowly propagate downward or modify the balance between upper cooling and deeper heat transport. The deeper gaseous layers would not respond quickly, but over immense spans of time they might shift in cloud altitude, circulation strength, or thermal structure. Seasons on such a planet would not resemble those of Earth. They would be drawn out across intervals longer than human civilizations, leaving the atmosphere to evolve at a pace that is almost beyond ordinary imagination. The deeper layers would also become increasingly opaque. In the upper atmosphere, sunlight and escaping infrared radiation can still move with relative freedom. Lower down, thicker gas and cloud material absorb and scatter radiation more effectively. This means the atmosphere begins to hide itself from view. The visible planet seen by a distant observer would represent only the upper accessible layers. Much of the deeper gaseous region would remain concealed behind clouds and thickening pressure. In this sense, the deeper atmosphere is already a hidden world inside the hidden world, not because it is separate, but because light can no longer easily travel through it. Chemistry in these layers would also grow more complex. Greater pressure and somewhat higher temperatures at depth allow molecules to interact under different conditions than they do in the cold, thin upper air. Methane, ammonia, water, hydrogen sulfide, and other compounds may occupy different stable forms at different levels. Some may condense, some may dissolve into surrounding fluid mixtures or participate in reactions that subtly change atmospheric composition over time. The exact chemistry remains uncertain because the planet itself remains hypothetical, but the general principle is clear. A thicker atmosphere permits richer physical and chemical layering than the sparse upper air alone. Gravity would shape all of this by holding the atmospheric column together. A planet of several Earth masses would retain its gases strongly enough that the deeper atmosphere could remain extensive across billions of years. Escape to space would matter much less here than in the uppermost levels. The deeper gaseous layers would be a durable part of the planet's planetary identity, not a temporary shell. They would store heat, redistribute energy, form clouds, and create the broad meteorological character of the world. So this region of the hidden planet would be one of thickening gas, rising pressure, layered clouds, and slow but persistent atmospheric motion. It would no longer feel like a thin boundary exposed to space. It would feel like a true planetary envelope, heavy and dynamic, shaped by internal warmth as much as by distant sunlight. In these deeper gaseous layers, the possible world beyond Pluto would take on the fuller character of an ice giant, not yet in its hidden central depths, but in the broad atmospheric body that gives such a planet much of its visible and physical form. Below the thick gaseous atmosphere of the hidden planet, the world would likely enter a very different internal region, one no telescope could see directly, and no simple picture could easily represent. This would be the mantle and deep interior, the vast volume where gases compressed by great pressure cease to behave like an open sky and begin to merge into denser planetary matter. On a distant world of several Earth masses, especially one resembling a smaller ice giant, this region may occupy most of the planet's total volume. It would not be a solid shell in the ordinary sense. It would be a deep layered interior of compressed fluids, volatile rich material, rising heat, and slow internal motion. The word mantle here does not mean the same thing it means for Earth. On Earth, the mantle is mainly hot rocky material lying beneath the crust and above the core. On a hidden outer planet, the mantle would more likely refer to a broad interior zone made of dense fluid mixtures rather than familiar rock. Planetary scientists often use the word ice in a specialized way for outer planets. In this context, ice does not mean only frozen solid material. It refers to compounds such as water, ammonia, and methane that are common in cold planetary environments, and that may exist under deep pressure in forms very different from ordinary ice. Inside such a planet, these materials may become hot, compressed, and fluid rather than frozen. As depth increases below the atmosphere, pressure would climb enormously. The great weight of overlying gas and fluid would squeeze the interior into denser and denser states. Temperature would also rise. Even though the planet lives in the cold dark beyond Pluto, its interior would not be uniformly cold. Heat left from formation, heat released by slow compression, and heat moving outward from deeper layers would all contribute to a warmer inner state. This is one of the essential truths of planets. Their surfaces and atmospheres may be cold, but deep inside, pressure and trapped energy create a different environment entirely. The hidden planet's mantle would therefore be a world of high pressure and elevated temperature beneath a very cold exterior. This interior is often imagined as rich in water, ammonia, and methane mixed with lighter gases and perhaps dissolved rocky material. Under ordinary surface conditions, these compounds behave in familiar ways. Water freezes or flows. Methane can exist as gas or liquid under the right temperature and pressure. Ammonia is volatile and reactive. Under the extreme conditions inside a distant ice giant-like planet, however, these same substances enter unfamiliar states. They can become dense hot fluids, supercritical mixtures, or exotic phases not encountered in daily life. A supercritical fluid is a state in which the distinction between liquid and gas disappears. Matter still flows, but it does not fit neatly into either category. Such states may occupy large parts of the deep planetary mantle. Because the mantle would likely be fluid or partly fluid over much of its depth, it would not remain perfectly still. Heat generally moves outward from warmer, deeper regions toward cooler outer ones. When a planetary interior contains fluid material and enough temperature difference, convection can develop. Convection is the slow, overturning motion in which warmer material rises and cooler material sinks. In a mantle of dense, volatile, rich fluid, this process may transport heat upward across immense spans of time. The movement would be far slower than weather in the atmosphere, but it could be powerful in planetary terms. Over millions or billions of years, convection helps shape the temperature structure, chemical distribution, and even magnetic behavior of giant planets. The hidden planet's interior may therefore be layered not only by composition, but by how effectively different materials move and mix. Some regions may convect vigorously enough to carry heat outward in large-scale circulation. Others may be more stable, with layers arranged by density so that mixing becomes difficult. If the interior contains gradients in composition, meaning that deeper material is chemically different from shallower material, that difference can inhibit convection even when heat is trying to rise. This matters because the internal arrangement of layers controls how the planet cools over time. A well-mixed interior loses heat differently from a stratified one. The present internal warmth of the planet and the faint thermal signal it may emit to space would depend partly on this deep invisible architecture. Electrical conductivity may also emerge in part of the mantle. Conductivity means the ability of material to carry electric current. Under high pressures and temperatures, water-rich and ammonia-rich fluids can become electrically conductive. If such conductive material is moving through the interior while the planet rotates, it may help generate a magnetic field through dynamo action. A dynamo in planetary science is the process by which internal fluid motion creates and maintains a magnetic field. Uranus and Neptune are thought to possess unusual magnetic fields linked to electrically active fluid layers in their interiors. A hidden planet of similar general type could perhaps do the same, though the details would depend on composition, rotation rate, and the exact geometry of its conducting regions. The mantle would then serve not only as heat-transporting layer, but as a deep engine of planetary magnetism. Pressure would also change the chemistry of carbon-bearing compounds in the interior. Methane present in outer layers may not remain in the same form at greater depth. Under intense pressure and high temperature, chemical bonds can rearrange. Some theoretical work has suggested that carbon-rich compounds may separate into different phases deep within ice giant interiors. That process could influence the planet's density structure and thermal evolution. The exact behavior remains uncertain because direct measurements for such planetary conditions are extremely difficult. Still, the broad principle is clear. The mantle wouldn't be chemically static. Depth transforms familiar volatile materials into dense and sometimes exotic forms, reshaping the planet from within. The interior would likely store a great deal of heat capacity. Heat capacity is the ability of a substance to hold thermal energy. A massive mantle of dense fluid can absorb and release energy slowly, which gives the planet a long memory of its formation and evolution. Even after billions of years in the cold outer solar system, the deep interior may still be cooling gradually. This slow loss of heat helps explain why a distant planet can remain detectable in infrared light even when sunlight is extremely weak. The atmosphere shows only the outer response to cold. The mantle preserves the deeper thermal history of the world. The transition from atmosphere to mantle may also be gradual rather than sharply defined. In giant planets, there is often no single hard surface where sky ends and ground begins. Instead, gas becomes denser and denser until it merges into fluid layers that are no longer well described as atmosphere alone. On the hidden planet, this transition may happen across a broad region where composition, pressure, and temperature all change together. The visible upper world would therefore rest on no familiar landscape. It would rest on depth itself, a descent into compressed planetary matter without any ordinary shoreline between air and interior. Everything in this region would unfold under immense confinement and very long timescales. The mantle would not announce its presence through dramatic surface signs visible from Earth. Its work would be indirect. It would regulate the planet's cooling, support possible magnetic generation, shape density and radius, and determine how internal heat reaches the outer layers. It would be the quiet body of the planet, the hidden volume where most of its mass may reside in dense fluid form. In a world beyond Pluto, where outward appearance is faint and unresolved, the mantle would carry much of the planet's true physical identity. So beneath the cold clouds and heavy gas, the hidden planet's interior would likely open into a deep mantle of compressed volatile rich fluid. Warm under pressure, slowly overturning, chemically transformed by depth, and storing the long memory of planetary formation. It would be a realm without sky and without solid ground in any familiar sense, a vast concealed interior that gives the distant planet its bulk, its thermal persistence, and much of its unseen planetary character. At the deepest inward point of the hidden planet idea lies the question of the core and the question of origin. A distant atmosphere can be imagined, a massive orbit can be modelled, a mantle of compressed fluid can be inferred from comparison with other planets, but beneath all of that would sit the densest central region, the core, where the planet's earliest material and earliest history are most fully concentrated. The core is where structure becomes memory. It preserves, in compressed form, the conditions under which the planet first came together and the path by which it may have arrived in the far darkness beyond Pluto. The core of such a planet would most likely be made of heavier materials than the overlying mantle and atmosphere. In planetary science, heavy does not mean merely large in mass. It refers to elements and compounds denser than hydrogen, helium, and the more volatile materials that dominate the outer layers. Rock-forming minerals, metals, and dense high-pressure mixtures would likely contribute to the core's bulk. If the planet formed in the young solar system as a substantial body, rather than as a captured outsider, its core may have been the first part to assemble. Small solid bodies would have collided, merged, and accumulated until a central mass grew large enough to begin attracting surrounding gas and icy material more efficiently. That process is known as core accretion. It is the leading broad model for how planets begin to form in a disk around a young star. Dust grains become larger particles. Particles become planetesimals, small building blocks of planets. Those bodies collide and gather more material until a growing core emerges. In the inner solar system, that process can build rocky planets. In the colder outer regions, where water, methane, ammonia, and other volatile materials can remain solid, larger cores may form with a greater supply of icy matter. If a core becomes massive enough before the gas disk around the young sun fades away, it can begin to acquire a thick surrounding envelope of lighter gases. In this framework, the hidden planet would have begun as a solid growing center and only later become a fully layered world. Its core, then, would not be a simple sphere of ordinary rock. At great planetary pressures, familiar materials behave in unfamiliar ways. The central region could include compressed rocky matter, metal-rich components, high-pressure ices in specialized scientific usage, and mixtures that blur ordinary categories. Temperature would also be high, even on a planet living today in extreme outer cold. The core would preserve heat from formation and from continuing compression under the weight of the world above it. The deepest center would therefore be dense, hot, and hidden beneath an enormous overburden of fluid and gas. It would not resemble the cold, frozen image suggested by the planet's present location. The outer darkness says little about the thermodynamic reality at the center. The structure of the core may also affect the planet's long-term evolution. A sharply defined, dense core can influence how the planet cools, how materials mix upward into the mantle, and how the internal density profile is arranged. In some models, the distinction between core and mantle may become less clear over time if the boundary is partly eroded or chemically mixed by immense pressure and heat. In others, the core remains more clearly separate. It remains uncertain which description would apply to a hidden planet beyond Pluto, because the answer depends on both composition and history. Yet in either case, the central region would remain the most concentrated record of the planet's earliest assembly. That assembly leads directly to origin. If such a planet exists, how does it arrive on so remote an orbit? One leading possibility is that it forms much closer to the Sun than it is today. In the early solar system, the giant planets and countless smaller bodies interact within a dense evolving disk of gas and solids. Gravitational encounters among growing planets can scatter some bodies inward and others outward. In this picture, the hidden planet begins among the zone where the known giant planets are forming or near it. Later, a sequence of strong interactions sends it onto a distant elongated orbit. If this happens while gas still remains in the system, or while many small bodies continue to exert collective gravitational effects, the orbit may be lifted and stabilized rather than ending in complete ejection from the solar system. The planet survives, but in exile. This outward scattering scenario appeals to many researchers because it connects the hidden world naturally to processes already expected in young planetary systems. Migration and scattering are not rare ideas in planet formation. Giant planets can move. Young systems can be dynamically violent. A planet may be displaced far from its birthplace if the early solar system passes through a phase of strong gravitational rearrangement. In that sense, a distant hidden planet would not require a wholly unfamiliar kind of event. It would require an unusually successful one, in which a substantial world is sent far outward but not lost entirely to interstellar space. A second possibility is that the planet forms far from the Sun, closer to where it now resides. This idea faces difficulty because the outer disk of the young solar system is thought to have been thin in material and slow in growth. At very great distances, orbital times are long, and collisions among building blocks happen less often. That makes the formation of a several Earth-mass planet in place much harder within the available lifetime of the protoplanetary disk. Observations and models generally suggest that building such a body so far out would be challenging. It remains uncertain whether special conditions, such as an unusually massive outer disk or local concentration of solids, could overcome that problem. As a mainstream explanation, in-place formation is usually considered less straightforward than formation closer in followed by outward displacement. A third idea is capture. The Sun likely forms in a stellar nursery, a birth environment containing other young stars relatively nearby. In such settings, close but not catastrophic encounters between stars can occur early in their history. Some researchers have explored whether a planet formed around another star could be captured by the Sun during this stage, or whether the Sun could seize a free-floating planetary body passing under favorable conditions. Capture is physically possible in principle, but it tends to require special circumstances and careful timing. It also raises additional questions about how often such events happen and whether the resulting orbit would match the properties inferred from the distant icy objects. For that reason, capture remains an intriguing but less direct explanation than outward scattering within the solar system itself. There is also a more cautious possibility. The planet may not exist at all. In that case, There is no hidden core and no hidden origin, only a useful hypothesis built to explain an outer orbital pattern that may eventually prove incomplete, biased, or caused by something else. This uncertainty belongs here because origin cannot be separated from evidence. A planet's formation story becomes scientifically meaningful only if the planet itself is real. Until direct detection or stronger indirect confirmation arrives, every origin scenario remains conditional. It describes what could have happened, not what is known to have happened. Still, within the hypothesis, the deepest picture remains coherent. At the center would lie a dense hot core, likely assembled from heavy material in the young solar system. Around it would build a mantle of compressed volatile rich fluid and a broad atmospheric envelope. Far outside, an elongated tilted orbit would carry the whole world through the cold darkness beyond Pluto. The planet's present remoteness would then be understood not as the place where it began, but as the result of ancient dynamical history written into a surviving world. So the innermost layer of the hidden planet is both physical and historical. It is the dense central core, where matter is most compressed and the trace of formation is most concentrated. And it is the question of origin, where planetary science tries to explain how a substantial world could come to inhabit so remote and faint a domain. In that deepest inward sense, the possible giant beyond Pluto is not merely an unseen object at the edge of the solar system. It is a test of how planets form, move, survive, and sometimes vanish into the dark margins of their own star's gravitational reach. Far beyond the familiar planets, the solar system remains larger, quieter, and less complete in human knowledge than it first appears. Its outer darkness is not a void of simple emptiness, but a region where time stretches, light fades, and motion slows into patterns that are only gradually understood. In that distance, certainty becomes rare. Small icy bodies drift through immense cold. Long unseen forces may shape their paths. A planet may be present there, carrying its own atmosphere, weight, heat, and deep interior through a silence so broad that even a world can remain hidden for ages. This possibility gives the far solar system a calm and unusual dignity. It does not demand spectacle. It asks for patience. A remote planet, if it exists, does not change the nature of the solar system by noise or brightness. It changes it by adding one more layer to an already vast structure, one more reminder that the sun's family extends farther into darkness than the eye can easily follow. And if no such planet is ever found, the search still reveals something lasting. It shows how carefully astronomy must work when the evidence is faint. The distance is immense, and the line between pattern and coincidence difficult to measure. So the outer frontier remains open, beyond Pluto, beyond the belt of known icy worlds, beyond the sparse edge of ordinary diagrams. The solar system continues in deep cold and partial shadow. There, matter moves slowly under the sun's weakened but persistent pull. There, ancient remnants preserve traces of planetary history. And there, perhaps, a hidden world continues its long orbit in silence, almost dark, almost still, waiting not to be imagined, but to be tested by the steady discipline of observation.